Just a quick mic check. We will be going live in 2 minutes. A warm welcome to all of you who have joined in right now into today's session, where we will go ahead and talk about how to become a financial data scientist. Finance is one of the most critical sectors in the world, and finance management used to require a lot of effort and time, but not anymore. Using data science, Now one can quickly analyze finance and make better decisions to manage finances. The use of data science in finance market has helped the industry in many ways. And to talk more about that, we have today Darren Lefcoe, CEO LEM Solutions Limited, and he brings with him his around 25 years of experience working in the finance industry and many more. So without further ado, let me go ahead and pass on the mic to him so that he can go ahead and get this masterclass kickstarted. Darren, the mic is all yours. Thank you.
Okay, good. Can everyone hear me? Or how do I know if everyone can hear me?
Yes, we can hear you.
Right. And can I share my screen here? It says you cannot start sharing while the other participant is sharing. I think you probably have to unshare.
Should we good now?
Okay, I just do share. Oh, there we go. Okay. Share. Right. I presume that you can see my screen. I can't see the screen being shared itself. I put my video on too. So can you see my background screen, Anne-Marie?
Well, I can see you, but not your screen. So
okay, in that case, let me stop my video. And can you see the screen now?
Just give me a minute.
Is that all good?
Yes, the screen is visible now, Darren.
Okay, fine. I don't know if I should put my video on or not then in that case, because I don't want to share the screen, or would my video go to the bottom?
No, you can start your video. That wasn't the problem. Yeah.
Then you can all see me as well, just to know that I'm a real human being. So we're all there, you can see everything? Can everyone see everything? Is that okay?
Just Darren, all good?
Good, okay, perfect. In that case, I shall start. So I'm going to be talking about a master's in data science. That's generally like the broad field. And just, well, a couple of things just to quickly cover. Just in case the internet connection does go down, I should be back within a minute if that does happen. I just noticed it happened earlier today, so once or twice, but it did reconnect quite quickly. So if that did happen, do bear with. By all means as well, I presume we'll have a Q&A session at the end. I don't know if that's the case or not, but by all means, do feel free. I'll open up the chat, in fact. Do feel free to kind of like put your hand up or chat or comment if you feel the need to, if you've got any questions or want to add anything before the end of the session. And I think that's it. I might just continue. There's a good, you might see from the bottom corner, there's like 80 slides I'm going to go through. Hopefully that means that it will take less than 2 hours. So we'll go with that. In particular, we're looking at data science in finance and investments. But the reality is data science is all over as well. So, and my particular background is in quantitative trading. I'll go over that in the next slide or two as well. And yeah, I've been doing that for the best part of a quarter of a century or so. So let's move on. I have a master's degree in physics from Imperial College London. I did that back probably just before the turn of the century. I had nothing to do with finance whatsoever. And it's probably a number of people here who may or may not be the same. Some people really care about finance, and others, just come from, science backgrounds, and it's all like find their way into it somehow or other. I ended up finding my way in by playing a game of chess with someone and beating them, and they thought I was good, but they weren't very good. And so here I am. But the reality is the quantitative finance space is quite similar to the science space and the engineering space. There's nearly no difference, apart from maybe in some cases if you're designing a satellite, you've actually got a physical object. But in many other capacities, a lot of the formulas are shared, a lot of the techniques are shared, and to a great degree, actually, the finance space, in terms of technology, quite often leads the engineering spaces and other sectors. So just something to bear in mind. And it's always there's always like a mini arms race in the race forwards, and that's probably why it lends itself to finance, kind of like pushing itself to the forefront. Whereas other disciplines, sometimes they need to exercise a tiny bit of caution. If you're building something, you've got to kind of like sometimes make sure that it works, but you can kind of like be a bit more gung-ho when you haven't got a physical object that's going to crash or something to that extent. So anyway, I'll continue. You've got my LinkedIn profile, so you can find me on LinkedIn if you did want to. I've also written a couple of books, one on Python programming, and like right now with Coursera, I'm doing a little course, a little master's degree for some people on Python coding. So I hope that's going well and they enjoy it. And that's going to be like part of the basis of this talk. Like, it will come in, it's about 10 or 15% of what I talk about, primarily just because the language is quite a useful language in the finance space, at least, or in the fintech space. It's just used a lot, and in particular, it's used because of its data science capabilities, and the fact that it's actually quite a good glue language for joining things together. The other book I've actually written, it's more about it's about the life cycle of a quantitative trader, and the kind of things that you will and won't go through. But it's maybe a bit more passionate and a bit less scientific, and there's actually like background to it, and it's sort of like the life aspect of it as well. So it's kind of like two angles. One is just your pure quant stuff. And the other side of everything that we do is kind of like how you build a business and other things around it and so forth. And we're going to kind of like be looking, towards the end at least of this chat, we're going to be looking at it's like where the future, or what the future holds for us. So that's kind of like our sort of like end goal, like when we've like inspected and looked at all the things that we've done in the past and the things that we can do and the environment around us. It's sort of like where are we heading, and what tools kind of like do we need going forwards. So fintech in general, finance and technology, I guess it's just got related fields. It's obviously got the finance field, it's got the technology field. Technology has like largely taken over in many aspects. Obviously the databases, connectivity, latency, which refers to speed of connectivity, all of these types of things, big data, processing of big data. So when you pull in big data, the timescales that it takes, real-time computation, that's quite intensive. There was like one of the last kind of projects that I was on. We're taking a couple of thousand items, like prices of bonds, and we're kind of like working out an average, but which is actually quite computationally relatively easy, but then we're trying to do it in real time. So all of a sudden, what appears to be easy, and you've got a little bit of time to do a computation, you're trying to do this multiple, many times, per second, effectively, over many instruments, and it becomes a lot more complicated, as you go deeper and deeper into this. Maths is the basis of pretty much everything, nearly always, for all sciences. It's the language of all sciences, and that includes computing. Everything's the fundamentals all come from that, and then we kind of move into the physics aspect of it. And from that perspective, again, it's kind of like physics is like the natural way that we look at the world and like how we can model it and so forth. It's language is maths. So as a physicist, we're talking mathematics effectively. And we just, we share, there's a lot of things. And I was kind of like when I first, when I was studying, I knew nothing about finance at all whatsoever. And I cared about quantum mechanics and general relativity. And you do things like the wave equation and heat equations. And you don't actually realize that there's, or you do later on, but there's strong parallels between a lot of the differential equations that exist in physics and those that exist in finance. And if those equations don't exist, like the concepts do, they're kind of like transferable. And generally speaking, like, in the fintech space, you'll have a lot of these types of people. And of course, finally, engineering. I've never really studied engineering, but engineering is like a part of everything, nearly. You need to, whilst maths and physics, they're kind of like the theoretical aspects of it. At the end of the day, engineering is closer to the computational part, where you just need to do things like get your code running, literally get a hello world application running to get it up and operating. If you're working in the cloud, get yourself into the cloud. Sometimes you're trying to link up files or databases and they don't link, sometimes for really obvious reasons like passwords or something don't link up, and other times, the plumbing or path names for files, and just getting those things right. And quite often, again, like not overlooking it in any way, but like any kind of like slight mistake or like oversight somewhere, like you're looking at the wrong file or something, all of a sudden you can have what is it, stale data or bad data in some way, and that's going to affect your performance. It's going to affect your calculations, and it's going to affect finally at the top level your P&L and everything that's kind of like important to you. So that's kind of like a brief overview and introduction. We're going to keep going through, and we're going to kind of like migrate a bit more into the data science part of it, and the kind of things that you'll come up and see and so forth. And the first thing is, I guess, the technology. I kind of like mentioned it already in the previous slide, but for us, at least for the data scientist or for anyone, any practitioner, engineering is, in the way that we're doing it, it's coding and a lot more. So like getting the hardware and the software to kind of like all work together, whilst you don't have like you haven't got self-automated driving cars. You've got large networks and connectivity and other things, and quite often, like in some of the organizations that I've worked in, it's ranged between, some of them have been like a dozen people, like a small fintech type of place, but other ones have been like 50,000 people. I've worked in one organization that's 150,000 people. So you all of a sudden, this is way more than the individual. It's like a small army that's moving around, and each part of that has its own component and needs to fill its own space. When we talk about engineering and we look at the coding aspect of it, I put 3 up here. I've got C++, Python, and Node, which is JavaScript. Node.js, which is sort of like the back end of JavaScript. But there's many more languages. There's also like Java, and there's literally tons of them. Each language, there isn't one that supersedes another in some way, or is better or worse and so forth. Most of the languages can do most things. However, some are more suitable for doing certain jobs than other ones. A bit like if you just opened up kind of like your toolbox, and I don't know, you wanted to put a picture on the wall, you'd kind of like, you'd need a hammer and you'd need nails. You wouldn't use a screwdriver and you wouldn't use screws. So it's kind of like, it's probably a crude analogy, but the languages, that each of them have their own kind of like their fortes as to where they're good at. And knowing and understanding this is quite helpful. The first language that we look at is probably like, it's kind of like close to the father of all languages, which is C++. It's the language that has curly braces. So all of the curly brace languages and semicolons at the end of the lines. It was an early language. It's compiled and it's close to much closer to the computer's core than other languages. That makes it fast. But you have to do many things in C++ that can kind of like make it a bit more complicated or slow the constructing time down. So not the actual execution of the code, but actually the person writing the code. It just has to be a bit like larger and a bit more kind of like verbose and I'm going to say complicated. It might be a harsh word, but it is a bit more complicated, kind of like using that language. But at the same point in time, you gain a huge amount of speed for it. And many people who code in C++ might not even touch any of the other languages. One of the things, obviously, that you have to do, for example, in C++ is if you've got like variables of your various kinds, your integers and floating point numbers and so forth, you do have to declare them before you use them. It costs you like lines of code effectively, so your code is a bit longer. That does make it, on the other hand, more kind of like more robust or secure because you're less likely to overwrite a variable with another one. So it's got like these inherent advantages, but at the same time, the code is a bit larger and so forth. Then we move on to Python. That language, which has kind of like been adopted, at least in a lot of the front office environments, as sort of like the main language. And there's kind of like a reason for this. It is a bit slower. Yes, so someone's just asked a question actually. How do you, and also, can I go to slide 3? I'll open up slide 3 quickly. I'm not sure, was that the slide you wanted open? Or was it this one that had the books on it? But anyway, I'll leave this slide open for a second or two. Have we determined what language we want to use? It's kind of like, generally speaking, in all of the different fields that you're in, and it depends on what you're doing. If, for example, you're doing front-end web development, you're probably just going to use something like JavaScript, right? You can actually use Python. Python's got certain tools for web development as well. So it's got like Django and Flask. So it's got like its applications. But the reality is the bulk of the community who code in who do like front-end development, they pretty much all use JavaScript. All web browsers kind of like work in JavaScript. So they'll use that language, and the community's built up a whole variety of things that work very well in that language for that very reason. Like so you get this ecosystem, right? On the flip side, so you go back, if you're going to if you're on like when you're in like the data science space, quite often you sort of like want to display things. You might want to kind of like get your data into grids. They're called data frames, in a certain model in Python. And kind of like Python sort of like lends itself. You want to construct arrays quite quickly, or you want to build, you want to prototype. You want to prototype your modules or your code, whatever you're trying to do. You want to get that up and running quite fast. And a language like C++, you'll probably use that like later on in the life cycle. When you've prototyped and when you've proved your concept and got it working reasonably well, you might want, like when you want to get those like final bits of efficiency, you'd go to a language like C++. And again, like if you're like coding for gaming, you'll just use C#. You won't even use those languages necessarily. You'll use a completely different one. Again, you're using that for speed. So it depends where you are. And where do you use Node.js? It's the back end of JavaScript. It's quite convenient. It's because it's written effectively in the same language as JavaScript. It's JavaScript, on the server side effectively. And if you're doing it's that JavaScript is naturally asynchronous language. Asynchronous means you can do things in parallel. So when you're trying to do lots of things in parallel, Node like naturally offers this to to its user base, and that's quite convenient. So if you want to open many files at the same time and read them, that's a cost saving, as opposed to like, let's open one file, read it, store the data, process it, and then open another file, and so forth. And what happens if we're doing that in a chain of 100 files, and file number 20 breaks? So you've got like all of these kinds of issues, and Node naturally to like bypasses that. It's actually asynchronous because of its web behavior. It's always sitting there waiting for you to click on something. The user clicks on something, and then JavaScript springs into action. So Python is a bit more of a synchronous language, and I don't know if that leads me to the well, it kind of like does, yeah. It leads me to the next slide anyway, so it's kind of like a good question. Feel free to throw in your questions anytime. Python's naturally synchronous. It doesn't mean it can't do asynchronous things. There's modules that Python gives you the enablement for doing asynchronous programming. And if it couldn't, it would be a failure. Like you wouldn't be able to use a language. So Python enables threading, which is like sharing of the computer resource in a way that looks like it's asynchronous. It also lets you do multi-processing. So that's quite powerful. It lets you use different parts of the processor to compute different things. Generally speaking, you'd use multi-processing. You tend to use asynchronous programming for things like file input and output, that type of stuff, or requests to the web, where you can send many requests and kind of you have to wait for a response. There's a latency that's there. It might take you that half second or that 1 second to get the response back, and you don't want to accumulate that 1 second. So there's that asynchronous behavior, and then there's multi-processing, and they're actually are we getting any certificate after this masterclass? I don't think there's any certificates. I just think it's a generic class, and then someone just asked it, are we getting any certificates for this? There isn't a certificate, but I think it leads on. And if you're interested, there's courses basically, and you'll be able to kind of like, I guess, enroll or register in those. But I'm just giving the talk. So, but anyway, we'll get back to it. There's a difference between asynchronous behavior and like effectively the multi-processing. So if we've got an intensive process, not a light process, not many light processes, but like a few intensive processes, we might want to, and we want to run them from one piece of code, we might want to run them on different cores. So like, and this comes quite strongly into a lot of like the more advanced data science types of things, where like you've got the machine learning and the artificial intelligence, where the complexity of the code is quite large, and it wouldn't, like if you had to run something on one core and you couldn't run your other pieces of code on other core, it might just take like use all of your computing time effectively. So there's a balance in all of these things. On the other hand, Node is good for WebSockets. When you want to connect into an exchange, read the data, kind of like sit around and wait for the data. And in fact, before WebSockets came about, it was just HTTP requests. So what you would do if you wanted to check your price is you would fire in a message, be asking for the price, and you'd get a response back. And you'll keep firing in prices and getting response back. But that's changed over time, and WebSockets came into play. And the way that those work is you do a handshake initially, and then the code kind of like sits there and waits for a message to come in. And when a message comes in, it then goes into action. So something like a price comes in, and you've traded, and then you want to sort of like reset your prices and send new prices. Node is very good for that kind of thing. It's naturally asynchronous and it works well that way. Python has a module that does pretty much exactly the same thing. In fact, it's quite nice. It's called async.io, and it lets you do a very similar thing. So again, it's kind of like knowing what you can and can't use, and like that will determine what languages you select going forward. But generally speaking, in the data science field, Python, or in the finance field in general, Python is quite a popular language. It's relatively easy to construct things in Python quite quickly. It's easy to pick things up. And nearly you can think of sometimes that you don't need a language at all. You could use a spreadsheet, and a spreadsheet is your best tool quite often. If I said like, let's get the average of like 10 numbers, you just use a calculator. You might even do, like if I said get the average of 3 numbers, you do it in your head. But say get the average of 10 numbers, you might use a calculator or a pen and paper, because it's the quickest thing to do it on. If I said do like get the average of 100 numbers or 1,000, you wouldn't necessarily go to a programming language as your first port of call. You might open up a quick spreadsheet, knock out the 100 numbers and do equals average and get your average. So it's only like where you want to do more sophisticated things, but Python is kind of like that language. That's the next layer beyond spreadsheets and say VBA. It's like a general purpose programming language, and so it lends itself quite well to fintech and front office in general. And the question is, I guess, why fintech? Like, because you could look around and like, I'm sure like there's plenty of smart people. There's plenty of smart people in this, like, who are watching this video, and you can choose to do a lot of things, and it doesn't have to be fintech. I guess there's a couple of aspects. Number one, it's fun. If you kind of like, I'm not going to say gambling, although it is kind of like gambling. If you like that aspect of it, there's a lot of that. If you like trading, I quite like the electronic trading thing. It does get the endorphins going when like trades are going on and you've got money at risk. So you've got that side of it. But the other part is it's really interesting. It's really technically, I'm not going to say difficult. Difficult's a hard word. Difficult's a word that might scare people away. It's not difficult. It's we'll just call it interesting in the same way that if you were to get like a puzzle, like how do 3 people cross a river with only 1 person being in the boat and all of that kind of stuff, and you want to like fix that puzzle and get the optimal solution. Fintech is very much a space for that kind of thing, and it might also be, and it's actually growing quite a lot. It might be a hobby now. There's one thing, and I will get onto it later on in the slides, but one thing in particular is like the crypto space. All of a sudden, and this kind of like started, and I will go through it to a degree, but all of a sudden, in about 2008, 2007, post the Lehman crash and so forth, a new asset class came about. And we're able to, as users, we're able to harness that and kind of like, you can trade effectively on the financial markets, but on a 24 hour a day basis, 7 days a week, 365 days a year, never closed market. And the barriers to entry are very low in terms of you don't need to put in tens of thousands of pounds to execute a trade. So all of a sudden, like you can even be doing this kind of like as your hobby. And the other, I've kind of like mentioned it already, but there's just lots of challenging puzzles, and you've got like this goal that you want to get to, whatever that might be. Sort of like, I want to work out, just, the amount of tax I have to pay for the profits that I've made. And like, how do I do that? Well, I need to work out the profits. How do I need to do that? I need to work out like all of the sales minus all of the purchases. It's like, there's a whole bunch of these like little puzzles that you kind of like need to solve. And then you ask that same question and go, well, I need to do that for like 400,000 transactions, right? And I could work out the average for 10. That was quite easy. But now I need to do it for 400,000. I need a general idea. And it's kind of like, how do I do that as quick as I can? My code doesn't work and it's taking half an hour to run, and it should take like 30 seconds or 2 seconds. So how do I like get this thing to work faster and better? And finally, it is like, fortunately, I guess it's one of those hobbies, should we say, or something, or like vocations where it does pay quite well. So if none of the other things interest you, quite often, the last one that's colored in purple here is the one that might interest some people. And the reality is it's probably true to a lesser extent today. But when I was doing engineering, I actually ended up, for good or for worse, going into finance, just literally because of the multiples of difference in salary. So, and that's just something that I guess you can't knock, and it's there. So like you just say it and that's in the room. Is market variables a puzzle? How do you mean is market variable? If you want to elaborate on that, I mean, in general, the market is just continually evolving. So the entire thing is a puzzle. I'm trying to figure out something, and you're like, if you're trying to figure out like what to do next in the market, you're not going to get very far if you just can't like know how to do the basics and so like, oh, I can work out an average, because that's been done 1,000 times. So like the market is always looking for the next thing. You know, what's that next iteration, that thing that's going to put you like a tiny bit ahead for a short period of time until everyone catches you up again, and then you have to find the next thing that puts you ahead, and so forth. So it's a puzzle in that respect. You just got to figure out that next piece each time. And Python itself, we could pick any language, as mentioned. Most languages will do most things, but Python happens to be popular and convenient. It's what's known as a glue language as well. It connects loads of different things together quite quickly and very simply. Calling data from databases, pushing them sort of like into data frames, pushing data back up into databases. These are all done in just like 1 or 2 lines of code. If you want to read like a CSV or a text file, again, you know, it's literally about 4 lines of code. You'd import pandas as PD, and you'd read the CSV file, and then all of like magically kind of like a lot of it comes out. And even if the CSV file isn't formed that well, you know, the environment, the module that you've imported kind of like handles a lot of that, and like partly even goes to the extent of cleaning it before you've had to clean the data. And the community that's constructed this, Python was made it like being created in 91. So we're talking about 30-year-old language, but the community that's developed this is massive. And I might say this a few times in the course, but you'll discover that you're literally standing on the shoulders of giants when you use this language, and you begin to realize just how flexible and good it is. And I guess that's its kind of you know, that's its thing, should we say. But again, like there's many languages that are quite well developed, and you can do most things in most languages, and you could do a lot of your data science with never having touched Python. And you know, do nearly everything in Node.js. It will offer you, you know, the similar types of things. So with Python has a pandas data frame. Node.js has a D3, which is its own sort of like data frame, and so forth. And all of the different languages will have their parts to play. And kind of like going like sort of like back to the beginning, I will like jump around a little bit at certain points, but some of this is kind of it seems really babyish, but like when I walked into you know, studying a master's degree in physics at Imperial College like 20 or 25 years ago, you know, having got like all A's in maths and, you know, A levels and doing really well and all the rest of it, and you're sitting there in the lecture theatre and there's like 300 people in a room, and like they're all of the best people around, and the lecturer comes in, and the first thing he does is he writes this down on the screen, 0 + 1, or not on the screen, on the blackboard at that point in time, because like that's how things were done. You'd write 0 + 1 = 1, and you're kind of like looking like sort of like, why is this guy telling us like most basics of the most basics? Like we know that. And then like, then he puts an underscore underneath the number 1, and he tells you, well, that's a vector and it's going in a certain direction. And all of a sudden, like he builds up all mathematics and builds you up 3-dimensional mathematics and other things from this very basic stuff. And the maths is core to all of this. All languages, for example, they have, and it's weird because the number 0 never used to exist on the number line, which is like our most basic and fundamental number. And like people would count, but they had a problem with the number 0, and then it got created. And then people had a problem with negative numbers and they needed to be created. And then people had a problem with orthogonal numbers, or should we call them complex numbers, and they need to be created. And they were actually called complex or imaginary numbers because we still don't know where they exist, but they do exist, and they're used in engineering all the time. So we go back to these basics. In all programming languages, we have like a null or a nothing or a none. Python uses the word none. I think C++ uses null. I'm sure that Java uses nothing. But anyway, they all represent zero. And we have to know, literally, the data science course, at least the course I teach, we start at something like really, really beginning, really, really basic. What is an integer? Like, what is a floating point number? What is a string? And what is a Boolean, which is either in all of them. A Boolean is a 0 or a 1. And what do these things do and how do they behave in each of the languages? So we want something like a desirable behavior. We want something like 0 plus 1 to be 1. And then we want 0 minus 1 to be minus 1. So we want these types of operations, and they seem really easy. And the next question I ask is, we want 0 times 1. We want it to be 0. And quite often, I'll ask that question, what's 0 times 1? And the answer comes back will be 1. And I'm like, no, just have a little think about that for a second. And then we want to do 0 divided by 1. And that destroys every computer that you've ever known, this most basic, simple thing. Or not 0 divided by 1, that's okay, that's 0. But then we want to do 1 divided by 0. So we want to do the inverse of 0 divided by 1. And all of a sudden, we get this infinity, or it breaks our computer, or we get an exception or a broken case. So we kind of just need to get, one of the things we need to do in any language, whatever we're doing, Python's the same. We need to kind of make sure that we don't break our codes, don't get out of our edge cases, and have things that are rational. And also, just by extension, if I was to change this to 1 divided by 0.00001 with quite a lot of zeros in front of it, it might become unstable. And even to the point where, if I generate an array of empty values, because I did this the other day in quite a popular module called NumPy, and then I went to and I did print my empty array just to see, I wanted an array of 10 things of blanks. All of the blanks were filled up with these tiny little numbers, 10 to the power of minus 232. And it's that's that floating point error. Sometimes, or for the most part, it's not a problem, but sometimes it can break your code, these types of things. And they're things that we have to be aware of. And they're the fundamentals of maths as well. We want our computer system to describe the real world. So we don't want to truncate a floating point number sometimes, and sometimes we do. Sometimes we want to round things to 2 decimal places because pounds or dollars or whatever currency that you're using, we want it into, we don't want 15 decimal places. But other times you might want to do the rounding, we don't want to do the rounding too early or too late because we've over rounded. So they're things to consider. And then we move on, we've got physics. So we move from maths to physics. And it's there is just a tremendous amount of conceptual overlap between physics and finance. I mean, and in particular, uncertainty. There is one part, I wonder if it's on the next slide, yeah. Just uncertainty is, we don't know, we have stochastic random variables, right? It's a long phrase or whatever. But we don't this chaotic motion, and we don't know what the next step is. Our goal is to try to predict in some way. If we know that the price is going to go up, in 10 days time, we'll all be buyers. And if we know the price is going to go down in 10 days time, we'll all be sellers. And we want in some way to be able to measure this or get some characteristics or do something. But one of the things that we do know, and this is a physics aspect and not really even a finance aspect at all, is we've got these concepts, and I just call it drift and diffusion. But you can kind of and I do have a slide on this later on. You can sort of imagine the wind kind of blowing all of the particles in a certain direction. But generally speaking, we know that they bounce off each other. So they're kind of going in, if you picked any particular particle, it'd be going in like this random direction somewhere, like, and you couldn't like say which way it's going. And that's kind of like saying, which, if I pick a particular stock or share, is its price going up or is the price going down? And I don't really know, but I might be able to collect them into an index or collect it and look at it over a longer period of time. And I might be able to access or like calculate or observe this drift. And I might even be able to observe this diffusion between the particles, like, how dispersed are they? So there's just that concept. And like, one of the things that's transferable in physics is a heat equation. Like, so like you heat up a pipe and so like it does get hot at the other end. Like, so you heat up the left-hand side and the right-hand side gets hot at a certain point in time. And there's a migration somehow of the energetic particles from the left-hand side to the right-hand side. And we do feel that. And these themes, and it definitely happened during the Lehman crisis, the housing crisis, or the great financial crisis, this like diffusion does happen. And if you can observe it or measure it or calculate it in some way, then you can certainly gain an advantage or get an understanding of the system. So it's just a concept, and I just speak about it as a concept, and it's kind of like, we need to just be aware of that, and they're the things that we're trying to measure for. And it's a parallel here, which I never really ever talk about in finance on the trading desk, but I've kind of like, it's always sat in the back of my mind, like as someone who's done physics and gone to a trading desk, like, and those of you who have done like any kind of stuff, if you want to measure the position of a particle, generally speaking, you need to sort of like observe it in some way. So if I've got a chair in a room and I want to know where the chair exists, all I have to do is shine a light on it and bounce the photon of light into my eyeball, and I know that the chair exists. And the chair doesn't move, which is fantastic. The photon of light is not like, it hasn't got enough momentum to move the chair. But when I do things, if I want to, if instead of having a chair, so like a massive object, I take another small particle and I put that in the room, and I sort of like want to observe that, I now have to bounce a photon of light off of it. And that photon of light that's bounced off of the particle has then moved the particle itself. Right? So this momentum, so by me making this observation, I've changed the course of the system. And when we come into the trading world, quite often people do paper trading, which is kind of like, I'll trade on paper. I won't use real money and I won't execute. It kind of like fails to quite a large degree, right? It fails from its physical characteristic in the same way that position and momentum would. By transacting in the market, you are changing the market in itself. And you might be, and you're actually changing the market in a chaotic way. So you're changing it more than you realize. Now, you may have no change. Your transaction might be so small that it has no effect at all. But you would never know that. And in some cases, your transaction might bifurcate, like the butterfly wings. You flap your butterfly wings in Australia, and you set an earthquake going off at some other part of the world. So there's that aspect of it, which number one, you're missing. Then quite often you're missing things like just the dealing cost, the bid offer spread, like you're dealing through a transaction. You're missing out that. Then you're missing out your fees. The cost of actually dealing, like printing a ticket costs you like £3 or £10 to print a ticket. And I went through a period like at Commerzbank where we did thousands and thousands of trades, and then we got an invoice at the end of the month, and it was for a few million quid. And we're like why are we being billed so much? And they're like, well, it's £10 a ticket, and we didn't factor that in. It was kind of like, okay, then all small transactions, we're gonna sort of like change our pricing on it. And it's quite material. These things add up. They don't look like they're going to add up. They look quite minute. But when you replicate them thousands and thousands of times, all of a sudden they become quite big things. So the physics aspect is always there, nearly in every part of everything that you do. And it's even in the part of like latency and stuff. You're sending a signal in, and the signal is not instantaneous. It takes fractions of a second. It might take a second or two. If you've got a regular internet connection and you're still like trading and you've got your algo over the internet, it might take like 4 or 5 seconds for the message to be sent to be received by the exchange, and kind of like to send you one back, and the acknowledgement and so forth. So those things, they limit what you can do, or limits probably not the correct term to use, but like you have to appreciate the time scale and what you can do within those timescales. And that's there's a whole bunch of physics, and it manifests itself in many ways, into like all of these like data sciencey types of things. And then there's something unrelated and related, like I don't know which way you call it, but you've got human behavior, and like one of the main roles, or a main role of the data science is let's try and measure in some capacity the primary behaviors of humans. And we've got fear and we've got greed, like the two opposite behaviors, and market races at these points in time for various different reasons. Like greed, so quite often the market trends up slowly for various reasons, and then it crashes quite fast, and that's the fear factor. So you've got this like sort of like accreting greed factor coming in, and the market becomes overbought, and we try to measure those types of things. And again, you don't know when it's going to break necessarily, but you can kind of measure it to an extent and see the extent of overboughtness. And then at some point in time, you get this fear factor, and then it goes the other way. And then along with that, you have the crowd and the clustering. And again, that makes a difference, because you might have a crowded trade. Lots of people have all of a sudden bought the same thing, and they're all trying to sell it at the same time. And that has a massive impact straight away. And we tend to get these collapses. And we see these things happen. We try to predict them, but we can't predict them because it's stochastic and random. But we can predict them to the one thing that's certain is the uncertainty. It's quite like a weird thing to say, but the one thing that we can kind of like guarantee is that at some point is the things that we like don't know or can't predict will occur to various degrees, and we can measure those, and we can at least encompass those, and that's part of, again, what we try to do. Going back to human behavior, the herd can be good. That's crowding. So it's not necessarily a bad thing all the time. Sometimes, quite often, you want to go with the herd. You don't always want to go against the trend. The trend, quite often, like people say, the trend is your friend. It's a horrible rhyme. But sometimes, that trend might be very good and will be persistent for many years. And that's a strategy in itself. And other times, that very same thing that's good turns out to be bad, because when it goes wrong, everyone's in the same position at that same point in time, and they've all realized the same mistake. But it's kind of like, for some people, or the last ones in general, is too little, too late. And we kind of like, let's overlook all of this to a degree. What we're trying to do, or we try to build the tools to measure this. That's what we're trying to achieve in the fintech and the data science type of space. It's like we can measure to an extent how good or how bad it is. We can attempt to calibrate to various degrees, and we're trying to take all of our human emotion out of this and just do this effectively, computationally, as best we can. And if we can do it, then we're going to be relatively successful. Now, the other thing about humans is we have limits. We have human, physical, real limits. And we like to think for everyone that we're sort of like the best. And if you ask like, a bunch of people, in particular, like you ask a bunch of guys, in particular, if you ask a bunch of young guys, how good are you at driving? And even if they're quite modest, they'll kind of like say, like, if you asked 100, you'll probably get 75 saying, like, I'm above average. Like, I'm not the best, but I'm above average. But we know mathematically that 75% of the population can't be above average, because the average will change. So like only 50% could ever be above average. So we have these distortions in the belief of what we can do. We also, as humans, we tend to procrastinate. So we've got this psychological aspect to it. We need thinking time. Sometimes the decision is close. So it's kind of like right to have a bit longer thinking time. Like it's like a 55-45 probability. And so it's not so obvious when you take a first glance at it as a human being. Like, I don't know, take a deck of cards and you know, if I say, you know, they go from like the ace, which is number 1, to like the king, which is 13. And it, you know, if I pull out like a 2 or a 3, and I say like, is the next card going to be higher or lower? It's like the answer to that's quite clear. We straight away we sort of like say the answer is probably going to be higher, so we go higher. And if I pull out a king or something, or a jack or a queen or something, one of the higher cards, or a 10, we'll go like, well, the answer is probably going to be lower. So that's quite obvious. But then when we pull out like a 7 or 8, and I go like, even thinking now, like which one is it? Like which is the middle value of all of those? Kind of like, or a 6 or a 7 or an 8, like which direction do you go? All of a sudden you need this thinking time. And that's just with a simple pack of cards that's only got like 13 items in it, you know, as opposed to like a more complicated decision that might be something, you know, that you've measured in some way and calibrated on a stock or a share. And you like, at a glance, we can't do these things. And sometimes trades have just gone against you or haven't worked in a certain way, and you're put off. You're put off psychologically. And then we've got the physical aspect of it. And by the way, computers like have none of that. They just like are completely agnostic to it. They're rules based. They follow everything. And we will get onto that aspect of it, but they just don't have these fallacies that we have. And the other thing is, and it goes back to reaction times and things like that. Like people like to think that they can drive faster than they can and so forth. And we like to think we can trade really well. And like, you know, you see a price kind of like flashing. And quite often the prices flash because they attract our attention at the eyeball level. So before it's even gone into the human processing part of it. But even that flashing light that's coming to our eye has taken, we're nearly looking at the world like in historic terms, as in it's taken a fraction of a second for that information to get into our eye, even before it's taken another fraction of a second for our brain to process it. So we just have this physical limit that's imposed upon us, even if we're super fast. And like, you know, you've just had your 10 coffees and just woken up and you're at your peak. We still have all of these things, and computers have none of those things at all. So they bypass it. I wonder if I will get onto that at some point. So we move on anyway, and we go back to computing, and we just go like, we're going back to like what we'll call our base language, which is Python. And we like look at the basics of like what we have to work with. And in reality, it's quite simple. There isn't like, it's built up of a bunch of very small things. Like we just started with mathematics with the ones and zeros, until like we build up all of mathematics from there, like Pythagoras, triangles, like, you know, the area of a circle, pi, like, you know, how do you compute those things? Like they've all come from the most fundamental building blocks and basics that we needed, like in order to get there. And then they came one step at a time. In Python, we're starting from the fundamentals, and we have a few like basic data types, and that's it. We have a Boolean, and a Boolean is just a 1 or a 0. I didn't want to write anything extra on the slide, just to keep it like that. We have an integer. An integer is just literally 1, 2, 3, 4, 5, just a set of whole numbers, and the negative numbers as well. And a number 0 is an integer too. And that's all it is. And then we have numbers that lie in between the integers. They're floating point numbers. So pi is an example of one, but 1.5 is a floating point number. Like 1.5, 2.1, 1 million.1 is a floating number. And so every currency that we use, they all have like, you know, pounds and pence, or dollars and dimes, or, you know, or whatever it is. They will have the major part and then like the unitary part. They're all floating point numbers. So nearly everything that we deal with in finance, in the fintech aspect of it, quite a lot of those numbers will just be floating point numbers. Why is it worth mentioning? floating point numbers cost you more in memory to store because they're larger in terms of like, how many decimal places do you hold effectively? So they're just like, they occupy a larger, a slightly larger amount of memory. But we're doing this, remember, we're doing these things millions and millions of times, and that like slightly tiny extra bits of memory ends up slowing down our processes or costing us, in terms of storage capacity and so forth. Then we have another type, which is strings. They're quite important because they're for humans. They're the things that we might stick our floating point numbers in between in a string. So like, my name is Darren and I have £100. Like that 100 was computed, but the rest of this, the rest of that structure was a message for me, effectively. And we could use messages in like strings in different ways as well. Like for example, for currency names, they're strings. They come in, we need to read them. We need to understand what the different currency pairs are, GBP, USD. That means pound sterling versus a dollar, or EUR USD, euros versus a dollar, and so forth. And then finally, the none type, which is like, again, if we create a variable, but we don't assign it anything, it does exist in some way. It exists in the code and it's occupying memory space, but it doesn't have a value, so it's none. And it might seem basic, but there's certain points where we need this none and other points where we don't want the none. And sometimes like we need none, like none is not the same as zero. It's different. None means something isn't there, whereas zero means the value of zero is there. So just things to kind of like, just the very, very basics. And then we move on from the basics to slightly more complicated things, which are lists. Python has a concept of lists, which is a collection of objects. So here's a list like 1, 2, 3, 4, 5. That was a list that was written down. And then dictionaries is the other type of collection. It looks a tiny bit complicated, but what we have in a dictionary is a key and the value. We have this key and its value pair, nearly like in a regular dictionary. And these things are, they're kind of like lists might be a bit more obvious, but dictionaries are direct to the memory. They're super fast. So they're used quite extensively in Python and in other languages all over the place. And I guess a key example for a dictionary in particular is if I was looking at a list and I wanted to find, and this list was not sorted 1, 2, 3, 4, 5, and I wanted to find a number generally in the list, I'd have to literally search for each item of the list one by one sequentially, or come up with a searching method that would find something, and that would cost me computational time, especially if that list was like 1 million items long, like Facebook's list of people. Now, if I had a dictionary and I knew the key and I just wanted to get the value, I could go straight to the item in the dictionary. So that's O of N in terms of like computational complexity. Like I know where I'm going and I'm going to that specific part of the memory, and I achieve that fast without doing any searches. So they're the two types that are available. They're collections, and then they're called lists and dictionaries. They're concept. And again, Python, I guess one of the beauties of the language is it's made up quite simplistically. And this is literally an extract of how you declare a function. You define def my function. It's kind of like quite obvious. And here's a function that takes a couple of arguments, A and B. Python uses white space. It's quite clear and easy to see. But there's a block of code that's visually observed by like this white space. So it doesn't use curly brackets or semicolons or anything like that. And that's one of the things why it's adopted quite well. And it returns a value. So a function looks like that. It's pretty straightforward, easy to use, and highly versatile. Like functions are used all over the place for loads of things, and we want these things to be easier. And we can build, when we create our functions in Python, there's like lots of like nice little, well, niceties that you can have. Things like doc strings that describe what your function is doing to the user. So when someone comes back a year later and they look at this complicated thing, this thing builds up quite nicely, and you can see all of everything that's to do with it, and so like a full description of what your code was going to do. And that's very useful, like later on. If we have functions in Python, then we move on to classes. And again, all of the modern languages, they have this concept of object-oriented programming. It quite often comes under the acronym of OOP, object-oriented programming, where an object is like the best description of what an object might be is it's a collection of or it's like a stencil that can be repeated multiple times. Like the classic example might be like a car or a person. So if we take, for example, a car just as an example, in object-oriented programming, you might have a class called for car. In fact, this should be a lower C. I'll just change that because it will annoy me otherwise. You might have a class for a car, and the car would have certain methods and attributes. So cars can be of different color, but they're still all cars. A red car is a car, and a green car is a car, and a blue car is a car. So one of the attributes of a car is its color. Another attribute of a car might be its engine size, or its top speed, or the number of doors. So there's certain attributes that cars have, and they're different between all cars, but they're all of class car. So they all fall into, they all lend themselves quite nicely to this object-oriented programming. And likewise, is also cars have methods. If you press the accelerator, the car goes faster. So all cars have a similar method. Press accelerator, go faster. Press the brake, go slower. So the classes will have attributes and methods. So things that already exist in them and things that they can do. If we were to take that same example of object-oriented programming, say like a person, you can have different types of people. You can have an adult, you can have a child. Well, they're both types of person, they're both human beings, they've both got 2 legs and 2 eyes, but they might have different hair color or different eye color. They'll have different heights, different education levels, and so forth. And they'll also have methods again. People can become 1 year older, or a person can start running, or a person can start learning. So they're all like methods. And if a person learns, then their array of knowledge gets larger. So we could populate an array. So this whole class thing saves us a humongous amount of time in coding. And like literally every language has this object-oriented thing. And Python has its own version of it that's similar to many of the other languages, and it offers it in quite a convenient way. So again, it's a nicety to have, because if we wanted to make classes in Python, it's relatively easy to do. And the other thing is that everything in Python is an object. So everything is kind of like a class, even a variable. So Python like goes one step beyond object-oriented programming, saying like everything is an object in Python. It exists in a certain piece of memory and it does a certain thing. And then just some more things about Python, but after we've had our functions, which repeat blocks of code, and they do like convenient things for us. And after we've had our classes, we can collect these things that we do, and we can put them into modules. And we can access these modules really, we can make our own user-defined modules. We can make our own user-defined functions. We can make our own user-defined classes. But we can also access our own modules very quickly by importing them with the import keyword. And we can actually import other modules that were built by other people that contain tons and tons of really, like, in some ways, really good stuff, some really complicated things that are like massively labor saving for us. And I'll go into a couple of bits, but we can import these in one line of code, and we can use all of the methods and attributes that have been built up in these libraries that we've created, libraries that others have created, and we can use all of those quite conveniently in Python. So that's quite a massive use case. And the three, there's many modules. There's like about 30 or 40 inbuilt ones, or maybe even 100 or 200 inbuilt ones. But there's also thousands of importable ones. So if we want to like do things with facial recognition, you do OpenCV. If you wanted to do web scraping, you use requests and so forth. Python, and that's one of its attractions. It just has all of these things. For data science, there's three main ones, at least to start with, but there is others. NumPy, which is a numeric pi is for data arrays. Pandas, which is panel data, it's for data frames. And something called matplotlib, which you might guess from the name is a library for plotting, a maths plotting library, effectively. And then I go on to codes versus humans, right? Codes are faster than us. If I was to run this piece of code in Python, this for loop for I in range 100, print hello I, it print hello 0 to 100 in a fraction of a second. Literally, like, it wouldn't even be a second, it'd be a fraction of a second. Humans can't do this. We can't perform like code. Not only can we can't perform like code, but the code can do this all day long, 24/7, all the time, without sleeping, without ever making a mistake. Right? If I write down 100 numbers, I'll probably make 2 mistakes, 1 or 2 mistakes in 100 numbers. So I can't even get to 100 numbers. The computer can do this like thousands of times relentlessly. So we can't do that. The other thing is, going back to the earlier slide with our indecisiveness, our psychological behavior, computers are robust. It's just as simple as that. If I is greater than 100 in this example and j is less than 1,000, it will do this. It will execute this line of code. That's it. There's no procrastination whatsoever. It's pretty much instantaneous. It's not instantaneous, but it's pretty much instantaneous. You can do thousands of these operations or hundreds of these operations per second, many times a day, as many times as you like, 24/7. So we've got the this looping thing, this thing that stays awake, always working, never making mistakes, and also very robust at this same point in time. The decisions are just consistent. And so, like, if we've got things that we know for sure, like, and in that cards game example, automatically, within a fraction of a second, our decision is made and the answer's there and we're ready to move on. And if the decision was much closer, the computer, again, it's pretty indiscriminate and pretty accurate. It doesn't think twice about it. It kind of like does the execution and gets on with it. Now, there is one fallacy. If it does do the execution, gets on with it, if you've written bad code, it can also be quite punishing. So whilst we get all the benefits, we still need to be aware that things can sometimes go wrong, and we need to just have that in the back of our mind, how we protect against them. And then we go back in time, right? Just for the reason, because in order to see what's going to happen in the future, it's kind of like useful to see kind of like where we came from. And I've kept this really generic. I'm sure I've missed out like tens of ages in between, and my historic knowledge is not fantastic. But we started off somewhere in the Stone Age with fire and wheel and some basic tools, right? That's where we started off. And we kind of like, we've migrated and, we discovered metals and advanced tools, and therefore we could make weapons. And the Bronze Age people, they were more advanced and they could all of a sudden make better weapons and kill the Stone Age people. And, we went on and on. As time goes on, we've come to closer to where we are in our part of time. So we've moved already 300,000 years in mankind in these two lines of a slide. And we get to the Industrial Revolution, which is like a couple of hundred years behind us. And this is a point when machines start replacing people. It wasn't so much machines necessarily, it's more like if things were being centralized. Where like people were farming like 100 little farms in their houses, all of a sudden we're like, well, why don't we make one big farm? We'll introduce farming. or where like everyone was knitting like one little jumper in each of their houses with their own little knitting machine or whatever, everything. Well, why don't we make a factory that knits jumpers? And sort of like get the economies of scale. And that's what the Industrial Revolution was about. And people, rightly or wrongly, were worried about losing their jobs. But were they really losing their jobs, or were they becoming or being used in a better way? And we're going to see that like data science is going to do this to us. Should you be worried about losing your job, or should you be embracing it because it's freeing up your time to do something else? Like, why would I want to, knit a woolly jumper, that takes me like 4 hours to knit, when an automated machine can sort of like centralize it and knit like 400 woolly jumpers and give it to all of the 400 people, and then they can spend their time doing something better, inventing something better, or creating something, or even just exercising, going out for a run. And from the Industrial Revolution, again, I've probably skipped loads of revolution, loads of important bits of time. But we get to, I've just named it the Silicon Age, just because we had the Stone Age and the Bronze Age. And so here we go, the Silicon Age, gallium arsenide, and the introduction of transistors and microchips, and what effectively has led us now into where we are. We're very much in it now, like the digital era. So we're kind of like touching the edges of the beginnings, where like we still didn't, like, at least I know like a lot of the young people that are watching this, they probably don't care about like the early parts, but some people like lived through the transistor bits. And when transistors were first created, they were massive objects. The first one, I believe the first one was actually made in Imperial College, and they had to push it in a wheelbarrow. It was so large, so it's like a big object. And now if you look at your phone, you'll have billions of them in your tiny little phone that you hold in your hand. So, and we'll get onto that as well. So this new world, we're coming into this new world, and we've got technology, and we've got a data-driven world. And it's just as simple as that. It's data-driven. And we've come from what's known as like a Turing machine. It's named after Alan Turing. It's like an abstract concept, because computers weren't even created then. But the concept of what a computer could be, wouldn't it be nice to have a machine that could do this and this and this, like this set of computations for us? We'll call it a computer. So with this abstract concept, but slowly computers started to be born. We had vacuum tubes, and then we kind of had transistors, and these are like switches. And our switches started to get smaller and smaller. And what are these switches? These are the ons and offs, and they create our binary decisions. When they create our logic gates, our AND gates, and our OR gates. And this is all the fundamentals of computing. And from those things, like the more switches and transistors that we can have and that we can fit into a chip, the more kind of like decision-making processes we can do. And someone observed this, and someone known as Moore's law, someone made this observation, and Moore's law is something like, I noticed that the number of transistors is kind of like doubling every couple of years, and the cost is halving every couple of years. And everyone said, yes, that's true. But that will probably continue for 10 years and not continue thereafter. So like, it's sort of like that. And this thing has become known as Moore's law because it's basically perpetuated for the last 50 years. And where we've come from and gone to is just tremendous. And this is this is literally what actually not is going to, does already enable a lot of our data science, which would basically be impossible without it. But I just took this little snippet off the web, but, and I'm sure it's broadly speaking correct, but in 2020, there was more than 932 billion chips were manufactured around the world. So I kind of like saying it again, but like 932 billion chips. That is just in 2020. So that's not like 2019 and 2018 and what happened in 2021. And that bears in mind that there's only 8 billion people on the planet. So like, the number of chips per person per year is already 100 times. Is it 108, 80? No, it's 8. It's Yeah, it's a factor of 100 per person per year. So we each own 100 chips per person per year on average on the entire planet. But Moore's law, right? So this observation that the number of transistors in a dense integrated circuit, what the hell is one of those, right? It's the thing that sits inside your computer or inside your mobile phone, doubles about every 2 years. So our computing power doubles. And we just see on this chart that, you know, he made this observation in the early 1970s. And everyone was like, yes, it's going to stop by 1980. And when I was studying it in uni, I was like, yeah, it's going to stop. But it hasn't. I don't know when it does or if it ever does, but computational power is increasing and increasing at a rate at this roughly doubling, you know, twice per year. And we need this. We need this because our computations are becoming more complex. And with this, we're able to do more things. So we move on. Like, what can we do? Let's just take some simple statistics. So we get the average. If everyone knows what the average is, it's the sum of all of the numbers divided by the numbers. And then we get this standard deviation, which is some kind of deviation away from the average. So these things don't all lie with the average. All the numbers are like sort of like different. We can also do certain things like take the minimum value. So we can like look through our collection of numbers and find a minimum. We can find the maximum value, look through the collection and find the biggest one. And there's different mathematical processes or ways of doing this to achieve this at this fastest possible rate. The reality is we could do a lot of those types of things for small data sets. We could do that 10 or 20, you know, we could do that 30 or 40 years ago, right? We wouldn't have been able to do it as well as we can now, but we could do it. And again, like the example I brought up right in the beginning was if I said like work out the average of 10 things, we could do it. And if I said work out the average of 100, again, you could sort of like, even if you cast your mind back 30 years ago, you could kind of like, you could write something that would do it. It would be on a slower processor, and it might take you like 30 seconds as opposed to the fraction of a second it takes now. But nonetheless, all of these basic things that we perceive to be as givens, they weren't givens at one point in time. And we are at this point in time in data science, because whilst these things now seem quite trivial for us and quite easy and fast to compute, we can do it on like many different free things in free packages. Those things at one point in time were a challenge. And what now is a challenge, that doesn't mean we've got no challenges. We've just got new challenges, like bigger things. So we're going to build on top of these things. So computation, what is an average and how do we do it in a computer? Right? This is the mathematical computational way of computing an average. Yeah, the arithmetic mean A is the sum, this like little squiggly thing, it's the sum from I equals 1 to n of all of these numbers, AI, so all of the A1, A2, A3, all of those numbers, let's add them up and divide it by the total number of numbers. Now, a modern computer, like I can do that, knock that up in Python in a couple of lines of code as well. I can import the CSV file with like, you know, a million data points. In fact, I did it for 65 million people just to show that you can do an election. And I could do the whole process on my 300 quid computer or something within the space of, it wasn't even a minute. So like a tremendous amount of computational ability. And that kind of like, we might ask, why are we voting on paper slips and so forth? And like, you know, that needs to be removed from our system because we've got we've got the ability to do, you know, to do an election. We could do like, you know, an election every single day if we wanted to, at pretty much no cost. So some question to ask your politicians in all the different countries. At some point that will come about. Nonetheless, right, we've computed this average, and like people couldn't do this in the past, or you needed like a computer and it was a bit more expensive and you didn't have it, but now it's a given. I can do it in an Excel spreadsheet, I can do it in Python, I can do it like 100 different ways, pretty damn fast. Can even do it on the mobile pretty fast. So we go from the average, let's compute something like slightly more complicated, the standard deviation, right, which is the mean deviation from the mean. So it's the sum of these xi's minus mu. Now, mu is the population mean, which we calculated earlier in the previous slide, which we called the arithmetic mean. And we take this difference, like how far it is from this mean, and we square that, and then take the square root of it. That guarantees to give us like a positive number, and then we divide it by the total number, and we call that the population standard deviation, which is a measure of dispersion. That's all it is. And again, we can do this. We can do like n greater than 1 million. Like, so we can do 1 million numbers really easily, like really easily, less than a second. So we can means and say, well, things that we couldn't do before, we can do now, and they're taken as givens. And then we can like continue and like do a lot more than that. We go, well, if I've got these distributions, well, I can do, I can look at all types of distributions. And I just run through some of them quite quickly, but like they're things that are inherent that we've got. So we've got something called the Bernoulli distribution, a uniform distribution, a binomial one. I'll go through each one of those on a slide quite quickly. I'm just looking at the time, 20, we've got time. A normal distribution, a Poisson distribution, the exponential one. And I'll go through them all. But importantly, I've highlighted the log normal distribution. It has a special place in the heart of finance because when we get to the slide, I'll tell you. But the Bernoulli distribution, right? It can take any value, can take value 1 with a probability of success. We could say that's P, and it takes the value of 0 with a probability of failure, and say that's Q. And a credit default swap in finance, so that's like an insurance contract on a bond, effectively. It will have this characteristic. It either the bond survives and pays its coupon and lives into the next year, or the company defaults and you get some kind of recovery. That's the probability of success and the probability of failure, and you get a credit triangle from that. And personally, myself, even like, so this is not even other people, but I've traded £250 billion of derivatives based on something that is not far from the construction of a Bernoulli distribution, but like bootstrapped in like a bit, you know, a bit more elaborate than that. And that was actually written in VBA, so not even Python, so an even more fundamental language. And that's what it looks like. And here's our little chart, you know, for what that distribution will give us. We'll either have a success or we'll have a failure. So that's our distribution. Not very interesting, or at least like it's our basic. Then we go to a uniform distribution. Again, it doesn't look that interesting from the chart in particular, but when you roll a fair dice, the outcomes are from 1 to 6 because there's 6 sides on a dice, and the probability of getting those outcomes are equally likely. And we could sort of like create this distribution. The function of x is 1 over b minus a. That creates this equal distribution. And then we determine where x can exist, and x can exist between a and b, and a and b are both greater than minus infinity and less than plus infinity. So, and that's it. That's our uniform distribution. Again, not amazingly interesting, but nevertheless, it's there. Then we can a slightly more interesting one, the binomial distribution. And that's a distribution where 2 outcomes are possible, such as a success or a failure. So again, it's kind of like if we go 2 slides back, we have this success and failure in the Bernoulli distribution. And it's a whole bunch of outcomes. So like we flip a coin, and we can either get our heads or a tail. We can flip our coin multiple times. Now, if our coin is equally balanced, we get like this bottom distribution. Like some think that's nice and symmetrical, and if our coin was biased in some way, we'd get this distribution. So we're now beginning to see distributions that are maybe we could say like slightly more complicated, and you'll get like binomial trees and other things, and they're really interesting computationally, and they can determine a lot of stuff in a like closed form, like a quick computing method. So like quite like binary trees and binomial distributions. Anyway, that's the formula for it, and that's kind of like what it looks like. And this bit here is I thought I'd throw in a bit of Python language, and that's P is not equal to Q. So you've got this uneven distribution, and then P double equals, it means it's equal to Q. There we go. And then we move on to probably like the most popular, I guess, of mathematical distributions, but it's called the normal distribution, and it represents the behavior of most situations in the universe And that's probably why it's called the normal distribution, because like it's normal. That's what we normally see. Like not the bestly named thing, but like that's basically it. And the function of the normal distribution, slightly more complicated in terms of looks. You got e to the raised to the power of something, and it's x minus u. Like, so it's something distributed from the mean. Like we saw that kind of thing when we were doing our standard deviations before, divided by sigma, which is a standard deviation, and that thing squared to guarantee that it's positive. So that means it tails off at the end. This e to the minus thing, so we get these tails and the bump and this hump in the middle. And like if you look at that and like what is the normal distribution? Like if you just took the heights of people, for example, you know, everyone generally, all adults, they'll all sort of like have an average height, and most people will be that height. And if you're slightly shorter, you'll be at the lower end of the bell curve, and if you're slightly taller, you'll be at the upper of the bell curve. If you go to a country that's got like a wider distribution, you might have the same mean, like the blue one and the green one have the same mean, but the green one has a wider distribution, a wider variety. And that manifests itself everywhere. Like, you know, I was going to say heights, but like ages, like what's the average life expectancy? Most people expect to live till about, you know, 70 or 80. So that's the like the peak, and the average will be at 70 or 80. And then some people might die early, and then some people might live till 100. So you've got that kind of thing going on. That's the normal distribution. Then you've got another type of distribution that kind of like looks like a normal distribution in a way. It's called the Poisson distribution, and it's applicable in situations where events occur at random points in time and space. It's a bit more like a randomized one, and we've got this probability of something happening. So that's what that distribution looks like. And not finally, because we've got one more after this, but you've got the exponential distribution, and this looks like completely different from the other ones that we've seen. But the exponential distribution is widely used for survival analysis. And I've put there like just as a little reminder, kind of like to myself, but it's from, you might have like a machine, like a car or a manufacturing machine or anything else, and it's got a certain life expectancy, and you know, a car will last for like 10 years or 20 years before it starts failing. But likewise for humans, a human will live, we expected our probability of survival, you know, for the first, you know, few years of our life, for the first 10, 20, 30 years of life, fantastic. And then afterwards we start getting heart attacks and cancer and all the other things, or like some of us might live to like 100, you know, like 95, but then we'll just die of old age or something else with it. So that's just survival analysis. And when I was talking about the credit default swaps and the Poisson distribution and so forth, even though you had like a survive or you'll either live through that 1 year period, or you'll default, or the company will default. If the company did survive that 1 year period, it's still got to survive the next year period. And ultimately gets like collectively those the cumulative of the like the Poisson distributions or like the Bernoulli distributions, the cumulative of those actually ends up looking like this, because it's some kind of survival curve that ultimately that's the journey that you're that derivative is taken on, and it takes this type of format. And finally, like the darling of finance, the log-normal distribution, it is quite important. It's not just for finance. The log-normal distribution exists everywhere where negative values are physically impossible, right? It does have a big place in finance, because when you like trading stocks and shares, you can lose all your money, but fortunately you can't go into like negative equity, right? You can't lose more than the value of your share. So like the share prices behave or move on some kind of normal distribution. They'll have a mean and they'll have a standard deviation. And these three curves here, they got different means. This has got the lowest mean, this has got the next lowest one, where the peak is effectively close to the mean. And they got different standard deviations, like how diverse, you know, the universe of stocks is, or like its volatility in price. But what they all are bounded by effectively is the fact that they can't drop below zero. So it's the normal distribution with a boundary condition imposed upon it, and that's what's used in finance. It's kind of like the darling of finance. And then we move on, right? Deep Blue, I don't know if anyone's heard of it, but it was a computer, right? Deep Blue was a chess playing expert system run on a unique purpose-built IBM supercomputer. What was called a supercomputer in 1996, 1997 is now like, again, the phone in your hand is way better than this supercomputer. So what was a supercomputer then is just an old relic now. But in 96, when Deep Blue did come out, it played its first game and it lost 4-2 to a human. By 1997, it'd already beaten Garry Kasparov and became the world chess champion. And it's moved on, and we can't compete with computers anymore for chess. Because of the way the algorithms work. They're fast, they're relentless, they can see all of the different things. And we think we can see 10 moves in advance, the computer can calculate like 100 moves in advance now. Which was fine, because chess is still kind of like algorithmic. But then comes something called AlphaGo, and there's actually a video on this, and I encourage you to all watch it. It's fantastic. It really would get your mindset into the data science. But AlphaGo is a computer program that plays the board game Go, and I've never played it, but apparently it's a popular Asian game. The difference between Go and chess is that there's like close to an infinite number of moves, and you can't teach a computer to play Go in the same way that you can with chess, where you have to occupy or some sort of game theory. But anyway, this is closer to our time now and is much more relevant to us. But in 2015, the first computer Go program beat a human professional Go player, right? It only took 2 years later, 2017, it beats the world #1 ranked player at the time. And it's awarded, and I don't know what a professional 9 Dan is, but my understanding is that it's the highest ranked thing around. But importantly, on this AlphaGo, the first iteration was something called AlphaGo Master, and it was succeeded by an even more powerful version known as AlphaGo Zero, which was completely self-taught without learning from human games, right? So we've come into the aspect, or this now exists. It's not like it's a figment of our imagination and it's not there or something. This thing, without even in all of our like machine learning and all of that kind of stuff, where we sort of like show it many games and it learns from the games, this one taught itself without even having games. So it sort of like played itself and it was just given a bunch of rules and figured out on its own. But if you ever do watch the documentary, the way that it played the world's top player at that point in time, and the way that it beat him, it made a move that no human being could have perceived. And like all of the experts watched this thing and they're like, wow, this is a mistake by the computer. And they didn't realize that the AI had kind of like taught itself to a level that it got itself high enough. Now, AI is not necessarily taking over the world at this point in time. It just means that it's a better AlphaGo player than us. So our computer things still do one thing really well, but the AlphaGo thing can't make you a cup of tea, and the chess one can't go and sort of like drive your car. So they can all do their things like in parts. Maybe at some point, we'll get further on than that. That'll be a little bit scary, but maybe we head there. I try and move on a bit quicker just because of time. I'm going to take us back a little bit in time to the great financial crisis, but it's still relatively relevant. We had the collapse of Lehman Brothers and a couple of the other banks, Bear Stearns, get bought. But in effect, we had the banking system bailing itself out. And a whole bunch of people turned around and said, like, we can't have this anymore. Like this centralized system, centralized banking system, we can't have this kind of thing anymore, where there's key decision makers and they're sort of like making decisions to suit themselves and it doesn't suit the community. And out of this effectively was the invention of Bitcoin. So there's the one little icon that I've kind of like done because I'm not here to advertise for Bitcoin, but it's kind of like born out of this. Bitcoin isn't actually a coin in itself. What it was a proposal for a trustless system of electronic transactions, right? That's what it is. It's some kind of system that has some sort of hashing and some kind of complexity in it that you have to solve, that costs you computational power in order to achieve these coins or like transact these coins. And these things, I don't have them there. Oh, yeah, I do. These things sit on an immutable ledger that is public and open source. So we'll go into that. What do we have? All of this stuff comes about from the computational power that we get. Everything that like we're able to do now is derived from this, like our observation of Moore's law, like continuing to be true. And like if it continues like on its path, it'd be even better and better. We're able to do more and more stuff. But now in the modern world, and this couldn't be done like 20 years ago, even 20, 25 years, just couldn't exist. We needed an internet. We needed Tim Berners-Lee to create an internet. We needed a decentralized payment system of some kind, and that couldn't exist without an internet. So now we can have a fully decentralized payment system. Right? This isn't a Bitcoin lecture, so there's only like a couple of minutes on it. We need something that's like purely mathematical, that doesn't have any human involvement in it. There's no need to kind of like print money like Monopoly and all the rest of it. So let's just stick to something mathematical that follows a process and like is mined in a certain way, in the same way, and it's actually called mining, in the same way that you know, you mine for like metals and things like that. What does decentralized mean? It means there's no borders, no politics, no restrictions, no nothing. Any two nodes in the system can transact with each other, and they'll be observed by all of the other nodes in the system. And if enough nodes in the system agree that the transactions happened, it will be added at some point in time to this immutable ledger, which is known as the blockchain. And we've never had this in history. So all of our ledgers in history, ever since the invention of mathematics and everything that we've had, has always been ledgers like spreadsheets that we can, effectively databases, that we can enter and change their values of. And that could potentially just create problems. It could create fraud problems. So this is the first time that we've had an immutable ledger that's completely secure. And the costs of breaking into this system, you could corrupt it for about 5 or 6 minutes, would be billions. So there's no, you're more incentivized to break into a bank and steal the money. It's cheaper and more efficient to do that than to try and hack the Bitcoin system. You'd be like, you wouldn't be able to afford to do it. Computationally, you wouldn't be able to afford to do it. But anyway, we move on. We go to classical finance. We've like looked at some kind of like sidey asset class that existed that's like growing in the sidelines. But let's look at our classical finance, what we all talk about when we know fintech, which is property, right? We've got property in every country, like millions and millions of properties. So like in the UK, we've got Rightmove and like all of the data and analytics that need to be done for this. Like if you take an area like a postcode, and then like look at the average house prices and the dispersion of it, you can kind of like, there's a whole bunch of things that you can do, and you can see like the cheap areas and the expensive areas and all of this kind of stuff. Then we move into fixed income, which is even bigger. It's probably the biggest single asset class that exists. Fixed income is bonds for the most part, hybrids, convertible bonds, perpetual bonds, all of these types of stuff. And then there's derivatives on fixed income called credit default swaps, which is like insurance contracts on a bond. If the company defaults, then the insurance company will pay you out for the bond. In the same way that if you crash your car, the insurance company will cover you for the cost of the car. But in order to have insurance on your car, you had to pay a small premium for it. So a CDS was that on bonds. Highly mathematical. These things, by the way, are probably all best built in a way in Python. Python has a list, like the list object, and it's quite like flexible and easy to use. And then Python has the NumPy array as well. So that's why Python fits in this kind of stuff very well. And then you've got structured products as well, and a whole bunch of other things. Going on from that, you've got equities. Again, like I'm not even sure I need to say very much, but you've got single name equities of all of the different companies, and you've got funds. These funds are humongous, like we're talking like billions and multi-billions in terms of like what's in the funds. And then you've got exchange traded funds that again trade like equities. An exchange traded fund, some of them might have several hundred or several thousand equities in them. I know that some exchange traded funds that I've done for bonds have had like 6,000 bonds in them. Other ones have like 200 bonds, but nonetheless, these collections of things, so we can measure them. and we can do these dispersion type of calculations in the same way that we could, that when I talked about the wind and like how it moves, it's like there is something at the data science level that we can do and measure. Same again for foreign exchange, probably another asset class that I don't like. I'm just looking at time that I don't need to go into too much. Like it's kind of like speaks for itself. Where you've got all of these major pairs, so like pound sterling versus a dollar, dollar versus a euro, euro versus a yen, and then you've got all of these minor foreign exchange pairs. So it's like all of the other currencies that you have to cross in some way because you're going on holiday somewhere from like one country to another, and you need to do exchange, or you've got big business going on and there's big transactions going. Same thing again for commodities. You've got metals, energies, derivatives, a whole bunch of things. And finally, again, we already touched on this, but you've got a new asset class, which is the crypto space. And it's best described as money of the future. When we used to use, back in the like thousands of years ago, we used to use coffee beans and stones for our money, and then we kind of like migrated to like little metal pieces or other bits like that, and gold. And then someone invented paper at some point in time, so we no longer had to carry around these stones and gold. We now live in a digital world. Crypto lends itself to the digital world. Like when we're transacting, we're doing everything kind of like in the cloud, and we want this immutable ledger. All of these things, we want the extra security that it brings us. Our old classical type of finance, a lot of it is now inheriting from the crypto space. The crypto space is superseding it in the same way that the internet superseded in some way, the printing press. So we don't use books as much, and we use the internet a hell of a lot more. And that's the migration. That's where we're trending towards. So classical finance, there's literally billions of volumes. The reality is it's probably trillions. And there's millions of transactions every day. And again, there's probably billions of transactions, but certainly millions of transactions per day. And even like on algos, like even when I build an algo at home, let alone when I do it like industrially, I'll trade, like I might do several thousand transactions. So like, and that's just on like an average computer, like in the house, let alone like doing something industrially, like on a trading desk. And that happens for every asset class. Like I look at one asset class, like, I've been in the bond asset class or the fixed income asset class. And yet there's like several of these things that are bigger, and one new asset class as well that's evolved. So there's plenty of space for us to do things in. In data science, where are we heading for data science? Right? We've got data analytics, or at least what we're looking at in data science. We've got data analytics, we've got artificial intelligence, we've got machine learning. I've thrown in Monte Carlo because it's like a complex process that's becoming easier. But all of these things require significant processing power. So I put it in like, purple or whatever at the bottom, right? We can't do any of these things without processing power. In the same way that if I gave you, any of those distributions early on, and so like said, work out the mean and the standard deviation, like 30 or 40 years ago, you would have struggled to do it with the processing power and the tools that you had available. Well, the same thing's now going to happen to us in artificial intelligence. Is happening in artificial intelligence and machine learning. Like we've built on all of these standard deviations, means, and all of this simple classical stuff that we did before. We take it as a given. We do them all in fractions of a second. Now we've moved on. We're going to try and do like more complicated stuff. Well, guess what? That comes at a cost, and the cost is processing power. And back to physics, so I've mentioned this already, like which direction is a given particle moving, right? And it's kind of like our utopic question or whatever. We don't know. They're all moving in their own kind of like random direction, bouncing off of each other. And then we apply a wind, right? And we can we don't know which direction any particular particle is moving in. But what we do know is that we can measure the average and the standard deviation of the group of particles and where it's moving. So we know the direction of the wind. So whilst I couldn't tell you where any particular air molecule was, if I was walking towards a hurricane, I would feel it pushing back on my body. And we can certainly measure this. And that's kind of like a large part of sort of like, or one of the beginning parts of like why and how and where we can begin to use our stats and our data science. And in data science, we measure and predict outcomes based on large data. So we're looking at big data. So again, that question of the particles didn't really work if there was like, 10 or 20 particles like what we've got in this picture, but it works when there's millions of the things moving in a certain direction. So we're looking, this bigger picture, it requires big data. This big data, well, all of a sudden you've got to store it somewhere. Our storage capabilities have gone up tremendously, like literally tremendously. Like whereas we were using cassettes and floppy disks like 30, 40 years ago, and then we sort of like migrated to CDs, and that was like 10 times better than hard disks. We've come on many ways, and like the first hard disk for like a megabyte or something, like now again in your phone, you'll have a tiny little chip and it'll be a gigabyte or 8 gigabytes or 10 gigs. And in some cases like 100 gigs. So we need tools for this. And as the tools get better and as our like capabilities get better, we get better and we can do more things. So like all of these things that were conceptual in the past, like even 5 or 10 years ago, we're now being able to do some of this stuff. And we can do it with Python, which is the good thing. Python is a popular language for data science, and this is kind of like where it begins to stand out. Or why, if you look at charts of like which languages have been the most popular, all of a sudden, Python has kind of like raced towards the top, and it was kind of like dormant for a while. And it's this increase in computational power, and combined with the fact that Python has like this like nice language and already sort of like pre-built libraries for some of this data science type of stuff. It's the product of those two things that have brought it to like its popularity. And in particular, like starting from the beginning there, we have NumPy, numeric Python, and it's for arrays. That's one of the modules. So we have Pandas, panel data, and it's for data frames. It's another thing for sort of displaying data. And then we have another module called Matplotlib for graphing tools. And then we have another module, scikit-learn, and each one gets built layered on the next one and so forth, and leverages it and fits into this community of things that gets done. We have scikit-learn that's used for machine learning. So Python modules. Python has many modules, and they're built by a large community. And here I show some of them: SciPy, NumPy, Pandas. From the names, you might be able to guess what some of these things do. Matplotlib, TensorFlow, Keras, PyTorch, scikit-learn, and it like the list is kind of like endless. And I go like, this is probably small. I don't know if you can read it on your screens, right? But this is how diverse things are. You've got a machine learning sector. You've got like 5 or 6 modules in here. Scikit-learn is the popular one in stats models. You've got deep learning, which is TensorFlow, Keras, PyTorch, Dano. You've got natural language processing. So that's to do with like, if I want to extract text information from like a report that's written, there's certain things that do that, and right at the top is NLTK. It's natural language. It probably stands for Natural Language Toolkit, but that's for natural language processing. And I've done that kind of stuff where like it's not just numbers that I want to see and analyze. If I get a report out, I might want to look for keywords and look for things like profit and loss, and like if there's the number of times profit is in a report compared to the word loss, well that might trigger a buy signal in the algo somewhere. So there's other things that we're going to do on the side that we haven't even thought about or didn't consider that we could do, that now we can do quite easily. Then we've got things like computer vision. That's not to do with fintech, but you've got things like OpenCV and scikit-learn. But if you do purchase the book, there's an interesting chapter that I do on OpenCV, which is one where OpenCV like lets you like do facial recognition, but not only does it let you do facial recognition, it lets you recognize objects. And I show in like literally only 100 lines of code. Obviously, I stand on the shoulder of giants. I've imported this OpenCV library. I can hold up like a pen, something like this, and it can recognize the black tip on the top of the pen, and I can sort of like wave it around, and it will draw on the screen. And it's kind of like I do it as a game, and I show you how to do it in the book. and I build upon it, and we sort of like get there, but the actual code to do that is literally only 100 lines of code. Okay, I had to do a lot of learning and understanding to get to that 100 lines of code, but it's done that easily in Python, and it's that convenient. And I show this game, and then you can hold up 3 pens and sort of like wave them around and sort of like write things on the screen, which is how a lot of our games are played. Like now, like when you play those games that are remote and you're holding the controls, and you're no longer like using like a remote control that's wired up to the computer, so it's done like in a different way. Then we've got things like reinforced learning, chatbots. Again, like there's tons of things here. Down in the bottom left-hand corner is the stuff that we were talking about, and that's a bit more relevant, which is data processing, NumPy, Pandas, and Skype, web scraping. I've done a lot of. There's a truckload of information that just exists for free on the web. Beautiful Soup is probably the main module. There's also, I don't see where it is on there, but there's other modules as well that let you do that. Audio analysis, the same thing. You might want to be able to sort of like listen to someone, not just read data that's written in the report, but maybe listen to what's being said. Like on a conference call, and kind of like digitally capture the bits that were important and kind of like translate that into a transaction in some way. PDF libraries, same kind of thing. Data visualization, again. These are for like displaying our stuff. So we've got Matplotlib, Plotly, Seaborn. These are all like, how do we, so like when we've computed the answer, sometimes you want to transact, but other times you might just want to show it to someone. So we've got that kind of thing. Data validation and operational research. But anyway, the point is I could go on and on and on a lot on that, but we can just see that it's vast. There's just like a lot of capability. In terms of data formats, what do we want to access, right? We want to access the World Wide Web, right? It gives us lots of data, right? Python lets us do this really quickly. Where else do we get data? XLS files, CSV files, text files. We want to be able to open these up and pass the data some way into our system really quickly. Another thing that we want to do quite often when we get bigger than data files, something like growing in size, is we want to go to databases. They're physical databases that we either own and sort of like manage and contain. They could be on your local PC or in the PC in your office, or they can exist now in the cloud. So that's something new as well, like the Amazon Web Server, Microsoft Azure, and Google Compute, whatever. And then other formats, social media. So there's truckloads of data coming in from social media. Can we harness it in some way? I've written Twitter bots and I've written LinkedIn bots and other things. Can we capture and put in this data, or we can pass out data in some way? And again, our mobile phones are things that we hold in our hand. We can't ignore that. Tons and tons of data that we're effectively, to the large part, like if you live in Europe or the Western world, at least you're giving it to Google. Like if you live in Russia, you're probably giving it to Yandex. But like each part of the world, like someone is collecting your data somewhere and they're selling it on it's extremely valuable. And how much data is there? So there you go. There's a number that none of us have seen before. 2.5 quintillion bytes of data. And I went and Googled it just to sort of like get that number of zeros to like what the hell is a quintillion? Because I want to tell you what a quintillion is. It's that number there. And I can't really tell you what quintillion is because there's so many zeros. So I went and looked up what a million looks like. And the million looks like this. So I can show you what a million looks like. And we've got a bit more of appreciation. And it's kind of like a millions. So that's how much data is produced every day. And there is something that, like, some anecdotes that more data was produced in the last few years than all of mankind that preceded the last few years. And that's probably going to continue. So the question is there a job to do for the data scientists? Is there a job that you can do? And like, let's have just a very broad, quick look. How much data is generated every minute? I've just pulled this straight off the web. 41 million shared messages on WhatsApp every minute, right? Video and voice calls every minute. So there's 1 and a bit million video and voice calls every minute. Hours of stream video on Netflix. So Netflix is not this company that like kind of like gives you just films and videos. It's a data intensive company, and it's probably more data intensive as a company than most trading businesses. It's like a data business in itself. Stories posted by Instagram users every minute, 347,000 of these. Can we harness this? Can we do anything with it? Messages shared on Facebook, photos shared on Facebook, 147,000 photos every minute shared on Facebook. It's just tremendous numbers that we look at. And if you accumulate them and add them all together, it's even more kind of like mind-boggling. And again, is there a job to do? And so like, here's the estimated data consumption, and we're now kind of like forward looking rather than backward looking, 2021 to 2024. Another number that I don't even kind of like can't tell you what it is, but a zettabyte, which is 1 billion terabytes of data. And a terabyte is 1,000 gigabytes of data. And a gigabyte is, I can't remember what a gigabyte, like 1 billion bytes or something like that. It's just a tremendous volume of data that's passing us. So the question is, let's go to slide number 3. Again, is there a job to do? 2 trillion searches on Google by the end of 2021. So we've had that. So we've had 2 trillion searches on Google. Volume of data created every day, 1.4 trillion of that. Email sent. Even though 67% of the emails are spam, still 3 million emails sent every second. So there's 1 million useful emails sent every second. So even if you took like the 1/3 of it, it's just a tremendous amount. Global IP data, so like IP addresses, again, like, 278,000 of these things, petabytes per second, and so forth. Again, the numbers are just large. So is there a job to do? And the answer is yes, there's plenty to do. Like there's like a ton of things. You just got to find the right space in data science. And then we go into machine learning. I'm kind of like coming towards the last couple of minutes. I'm really going to fly through this. Machine learning is a subfield of artificial intelligence. This is what we care about, and it's broadly defined as the capability of a machine to imitate intelligent human behavior. So what does that mean? Like we want to replicate what goes on in our mind. Artificial intelligence systems are used to perform complex tasks in a way that is similar to humans, how humans solve problems. We're trying to replicate our mind. So similar to how humans solve problems. That's kind of like our key thing here. And we go into machine learning, and there's 4 categories, and I'm going to fly through them quite quickly. But there's supervised learning, unsupervised, reinforced, and semi-supervised learning. The top 2 are kind of like the major 2, but we just kind of like briefly go through them. What is supervised learning? It's applicable when the machine has like some sample data. So we've got sample data, and you can sort of like use that to compute, outputs, and you sort of like classify things. So an example of this is, let's say that we've got a set of images, and the key part here is we've got a set of images, and they're all tagged as a dog. A machine learning algorithm is trained in some way to distinguish the images, so it can distinguish whether the image is a dog or not. We needed lots of data, lots of pictures of dogs and pictures of things that aren't dogs to say which ones are dogs and which ones are not dogs, and the machine can learn from that. And if we give it enough data and push enough things in there, then we can get this good this good learned algo. Unsupervised learning algo, on the other hand, is a machine is trained with some input samples or labels only, while the output is not known. The training information is neither classified nor labeled, so we can't like give it these pictures. We don't tell it if it's a dog or not, so it's a bit more problematic. And hence the machine may not always provide the correct output. So it can do things, but it's kind of like got to sort of like start learning in a way on its own. And an example of this is, let's say we have a set of documents, and we're trained. Let's assume a machine is trained with some set of documents having different categories. We've got these categories A, B, and C, and we have to organize them into the appropriate groups. Because the machine is provided only with the input sample, so there's no output, it can organize these data into types A, B, and C. So like it does some kind of classification. And then we got reinforced learning. We kind of like, we know what reinforced learning is in a way, because like if you're a kid and you sort of touch a hot kettle, you'll burn yourself and you won't do it again. Well, that's the computer's version of it. So reinforced learning is feedback-based machine learning techniques. The agents, in our case, a computer program, needs to explore the environment and perform actions. So it sort of like does something. And on the basis of the actions, it gets a reward, which is feedback, like positive feedback. And the goal of this, reinforced learning is to maximize this positive reward. All you want to do is get this highest score possible. So like if I score a goal and I'm 1-0 up, so that means I want to score goals. And like, how do I score a goal? And the computer figures out how to do it. And it just wants to achieve scoring loads of goals and not conceding them. Or driving a car around the track. So car racing around the track, and I've kind of like built a little algo to do this. The ones that sort of like go in a straight line just crash into the wall, and the ones that go in a curve learn to sort of like go around, and slowly like the ones that are able to go in curves, they're the ones that survive, and the other ones are all kind of like die. So that's the positive reward based thing. And then we've got semi-unsupervised learning. It's some kind of intermediate technique in between supervised and unsupervised. And it contains unlabeled data. I'm kind of going to fly on just because we've hit the 2-hour mark and I've got like 10 slides to go. Applications of machine learning, it literally manifests itself everywhere. Healthcare, marketing, self-driving cars, speech recognition. We know of some of these things already. Traffic prediction, image recognition is a big thing. Product recommendations, auto like translation, virtual assistants, financial predictions. And probably like, you know, for fintech, obviously we care about this last one, which is financial predictions. That would help us a lot in some way if we can do that kind of thing. And then we've got some machine learning algorithms, and I'll fly through them. But we've got linear regression, logistic regression. Linear regression, we could always have done. Logistic regression, case nearest neighbor, that's quite a nice, pretty looking one. K-means clustering, decision trees, random forests, support vector machines, SVM it's known as, and naive Bayes. And I'm just going to show you the pictures on these because we've run out of time. What is linear regression? That's probably the most obvious one of all of them. It's some kind of line, and how far we lie away from the this best fit line. I've done like tons and tons of this, and this was what we've done for the like past 10 or 20 years. So we're migrating on from this, but we're looking for the outliers. The things that are far away are like cheap or expensive or something to look at. And we want to flag these up in some way. Logistic regression is just like a little iteration on top of the linear regression, which is, it puts it into a category. So it's binary. Instead of like just being above the line or below the line, it gets assigned a value called based on a sigmoid function. And it's either true or false. So it's like false to the left-hand side or the right-hand side of that. And the decision or the logistic answer is based on that. The case nearest neighbor lends itself well to a picture. And a picture probably describes it best. But like, if I've got this blue point here, like I kind of like want to know, does it belong to category A or does it belong to category B? And if I do this classification of nearest neighbors, it looks at this point in time that it's probably a category A point. And certainly if this blue point was somewhere inside this zone of reds, I'd say it's probably, without knowing anything further about that data point, it's probably a category A item. Now, that's probably less used for fintech and more used for sort of like something on a production line. But nonetheless, it's a thing. Decision trees, they're kind of like used all over. They're quite efficient and quite fast. So they're quite useful things to have. And it helps us solve like classification things as well. Like it's kind of like got that classification thing where it's either true or false and you keep jumping to the next node. We might not think of this really as you know, some sort of artificial intelligence, but in a way it is. Like if you've got like many decisions and not just a few simple decisions, all of a sudden that's a complicated kind of like final answer that you might have derived at by having this like big decision tree. So it's true for big decision. Now SVM, again, something that like the picture probably paints the decision better or what it does better than I can describe it. But you kind of like created some kind of best line or decision boundary, right? And you sort of like classified the blues and the things. And then like you get this next point and you decide what side of the line it lands on. as to like which category it falls into. So that's kind of like a very 3-second thing on support vector mechanisms. And finally, so we're coming on to the last 3 or 4 slides, a neural network, which is a series of algorithms that endeavors to recognize the underlying relationships through a process that mimics what the human brain does. Our brain, we've got neural networks in them. I'm just going to go over a couple of slides that show you that. In this sense, a neural network refers to a system of neurons. That's what's in our brain. And it's either organic or artificial in nature. So the ones in our brain are organic. We're creating this, what we call artificial intelligence. And here is an example of a simple neural network. And it literally is just simple. You've got these things that come in, and that's called the input layer. And you've got this same type of, where was it back? If I jump back to this slide, we've got this same kind of sigmoid function that's happening in here, in these, in this hidden layer. Something's happening, and you collect these sigmoid functions, and you just you get a value that comes out of it. And that value determines what the output layer is going to give you back. And like the classical thing is like, you saw like if you write the number 3 on a piece of paper, it's like, can the computer recognize it's a number 3? And will it not mistake it for a number 8 or something else? And computers now with neural networks are tremendously good at this. They only need 1 or 2 layers to do this like extremely well. So that's our simple 1-layer one. That's what a neural network looks like. And a deep neural network is one that's got more layers. And the more layers that you have, obviously, like the computational complexity goes up massively, but the accuracy of your output layer, given the input layer, also goes up like tremendously. And the more that we can have of this, and the more processing that we can have, the closer we can have to effectively like a human brain. And kind of like that's kind of like where we're heading. So computational complexity, neural networks were previously unachievable from a computational perspective for us. Too long in time. They just took too long to perform, too many calculations. We couldn't do it. Our computers started getting hot and not working. Slowly, as our power is getting better, we can do this more and more. We can do this in different ways. We can have a mobile phone that's a small, low-powered handheld device. And what does it do? It connects to a large, powerful server somewhere in the cloud or somewhere else, and that does the processing and then sends us an answer back. So there's ways around these things that we can do, and that's kind of like the engineering aspect of it. This isn't just like a Python thing. Like there's a lot of engineering and thought that needs to go into it. Like how can we do the bits that we can't do? That's always the next challenge, and that's always the next puzzle. Like when someone asked me, like in the beginning of the chat, what's the thing? That's what it is. Finally, the last couple of slides. What can we do? As computing power increases, our ability to deploy more complex and computational intensive process increases. So we want this increased computing power is what's letting us do everything. And it's kind of like a double-edged sword, because the more we can do, the more we can figure out how we can do more things. So what can we do? We can already do a lot, and we will be able to do even more. Including things that we previously considered impossible. And I think that's the last slide. I raced through the last few to sort of like make time. But that's the end of it. Has anyone got any questions? Because I have come to the end of it. Do I need to hand over, or can anyone ask questions directly?
All right. Thank you, Darren. Yes, we are open to all the questions. And as
I know that I overran by 10 minutes.
All right, great. So we have a lot of participants watching us live on YouTube and LinkedIn also.
Okay.
So I'll just check if there is any question that we would like to bring up. Otherwise, all the participants who are attending the session today, it would be great if you have any question, feel free to go ahead and ask us. Thank you.
Okay. Okay, it doesn't look like there's any questions here. So, or there was one that was dismissed. Are we able to, to be on video meeting or voice meeting? Did you have a question? Someone's putting hi, but, and thanks a lot. You're welcome. I hope you enjoyed it. By all means, type your question in or even come on voice and ask it. Are we able to get them people on voice? Do I have to like do anything, or can you just jump in?
Yes, if you want somebody to, so that they can speak, you'll have to give them the option to allow to talk.
Right. How do I do that in that respect?
You can just go to that specific attendee and click on the button that says allow the talk.
Right. Okay. Let's see if I can do that in that case. Right. Why do I only see myself there? AB. Okay.
Right, Ayman, I have given you the access to speak, so I guess you can talk.
Yes, good evening. First of all, I must sincerely appreciate the excellent work you've done. This has contributed in no small way in my knowledge. And I have a foundation of finance, international finance, and some of the things I've seen this evening, they are quite related to econometrics, data predictions of data. So I want to find out, as a financial analyst, can I also imply some of the knowledge I have in econometrics to this? That's the question.
Yes, absolutely. But in what capacity were you thinking, though? I mean, the reality is it's kind of like unlimited what you can do. Like I've done things that are, I've done things where I've even, I had a bit of time and like I didn't want to open up all of the documents that were published by the London Stock Exchange and sort of like read the like the reports and what was in them. And I used kind of like that natural language thing that I was talking about, that NLTK. I didn't use NLTK. I kind of like did it on my own because I didn't know it existed. You can do all kinds of things, like anything that you can imagine that you can do, you can probably do. So, and I don't know what angle that you're coming from. You might want to elaborate on that.
Yeah, I think from what I've seen, I think it has to do. This has to do more of programming rather than the end user. For instance, from what I've seen so far, it's like building a software or building a machine that could solve some specific problem. And unlike the end user who will purchase these machines and use to solve their own problem. So issues of data, when you get data from the stock exchange, you analyze those data, know the direction. If these data, there will be a change in pricing in future, or you have reasons to, if you have, for instance, you talked about equity, the equity market, and also you talk about the bond market and other derivatives. If you have different kind of investments and because of the risk of losing it all in one market, you diversify. So how would you you can use the system, from what I understand, to diversify your investment in different asset classification, so that if there's a problem in one particular market, it doesn't affect the other assets you have. I don't know if I'm correct.
Absolutely, you can do this. In fact, like it's kind of like a recommended thing. And not only can you do this, but there'll be some modules as well on this kind of stuff because they'll be pre-built. You can compute like your efficient boundary. And when we talk about like exchange traded funds and those types of things, that's actually what they're trying to achieve at the outset. So and that's actually why that asset class on its own has grown a lot compared to other asset classes. You've got this crypto asset class and you've got this ETF asset class. And what is it? It's like this exchange traded fund. All of a sudden, where I would trade like one bond, I have this concentration risk. I have a name concentration risk, for example. Whereas where I trade an ETF, not only do I get the advantage that it trades on an exchange, so it trades in a different way, cheaper and more liquidly, but also at the same point in time, on some of these ETFs, there'll be like 1,000 or 2,000 securities that are in them. So I've actually automatically gained the diversity from the from trading ETFs, and that was manufactured itself out of a lot of this stuff. Now, if you're saying like, do you want to diversify between commodities and fixed income and so forth as well? You should probably consider that. Like, do you want everything in like the crypto space, and then with like there's a crypto crash, you lose everything, or do you want everything in the bond space? Well, if you have everything in one asset class, the bond asset class, you'll get a certain amount of returns, and you might want to enhance your returns, and therefore you go to the equity asset class, and you want to measure this like your risk-adjusted return, and that will form part of your computation in some way. As in, I'm willing to lose a bit more in order to gain a bit more, but I will do it to a certain balanced amount, and I want to calibrate what that will be. And I even want to measure between asset classes what that might be. So like I might look at the difference in equity premiums, like price to earnings multiples, compared to dividend, compared to coupons on bonds. So I might want to measure like the dispersion yield, or compare the coupons on bonds, so the yield on bonds to property returns. And so there's a whole variety of things that you can do. But that's kind of like, that will be dictated, number one, if it's you as a private investor by yourself, but number two, by like, if you're doing it for a company, it's kind of like dictated by the company. Like effectively, a framework for your risk limits is kind of like nearly what you're saying. And you know, I'll have a rule that will never let, and even if I was doing something like smaller, I'll have a rule that will never let me have more than like 5% of my portfolio in this one thing. So you might adopt those types of things. So absolutely.
All right. Thank you very much. Thank you.
Someone's asked, can I pursue a career in data science with a data analyst? What are the relevant courses I can do in addition to data science course to give me a hedge in the internal world? I mean, the first thing to do is a data science course is the reality. That's kind of like the best entry. I was going to say, like, you know, ultimately, if you want to be in kind of like fintech or whatever for the purpose of trading, you just kind of like need to get onto a trading desk in some way, and that's not course based anymore. It's kind of like it's buyer beware. So,
right, and just to add to that, Darren, we do have courses available in banking also, which includes investment banking, and that gives you the current landscape also. However, if we talk about the data science aspect itself, the courses that we offer are more or less comprehensive, that covers, you know, each dimension. So
and I guess I should also throw in the Python programming course, which is kind of like, I guess that's the core part of it. But like if you any coding course will certainly help your understanding as well.
Again, I tried laying my hands on the Python programming. It's a bit difficult because my foundation is not IT. I don't know if there's any way or any organization I can be recommended to have an interest in Python programming, please.
Did you do the course that I'm teaching now? Are you on that course at the moment?
No, I'm not.
Okay, I mean, because on that course I start right from the beginning. And we do get up to things that are like more complicated, but we literally start from like what is a variable. So that you're literally starting from the 1 + 0 part, and you see how fast that you do learn. So maybe that's a way to kind of like you know, get your way in. Again, like the book I wrote, I think when I started in the first couple of chapters, again, it literally starts from like, you know, what is an integer? What is a string? You know, what is a floating point number? And how can we add up two numbers together? Like how can we add 1 + 1? You know, and by the time you've got to like, you know, page 300, you've gone from like adding up 1 + 1 all the way to doing facial recognition. So it's kind of like you're not that many steps away on any of these kind of like basic kind of courses, you know, pick up the book, read it, like you should probably be doing them hand in hand, like all together, but you're probably not more than 10 steps away from being really good. And you kind of just don't know that yet because you've only taken step 1 and 2, and you don't realize that step 8 and 9 and 10 are actually just as easy, but they're just further down the line. So okay. Yeah, any of those basic courses, even the course that I'm teaching.
Okay, I'll give it a try again.
If you struggle, you know, ask for some help. Like And whenever I do the courses, like literally at the beginning of every single one, I keep on telling people like jump in and ask, because quite often the question that you don't like that you wanted to ask, there's probably about 3 or 4 other people that want to ask the same question. And like you kind of like, oh, I'm afraid to ask this question because it looks too stupid. It's actually like not only quite often is it a really good question, but it sort of like helps me as a person teaching, because I'm like, you just reminded me to tell you this kind of stuff and I forgot to tell you. And that's really important. So yeah, by all means, I think you should kind of like, do any of these kinds of things. And they're easier than you think, as long as you put the effort in. I caveat that with as long as you put the effort in. Anyone else?
Thank you, Ayman, for your question. Is there anybody else who has a question? Right, I see something coming up.
Yeah.
I guess you can take that question. It's from Isika.
I'm trying to figure out what an animal scientist is. That's quite an interesting space. I'm more interested in the interesting spaces because it's the diversity of kind of like how you use it. How would you use either Python or C++? Or again, I guess the real question is what are you trying to achieve when you say that you're an animal scientist? Like, what are you trying to find out? What are you trying to do? If you describe that, then I could probably answer the question better. I mean, my intuitive thought is just to tell you to that Python, because I'm kind of like thinking that you're measuring or doing some sort of like data analysis on the animals themselves or something like that, but I don't know. In which case, Python certainly lends itself better.
Isika, you do have the access to ask the question. So if you want, you can unmute and ask also. Martin, let's just wait for Isika and we'll come to you, Martin. Okay?
Okay, sure. I will wait. Yeah, that's fine.
All right. Isika, do you have something to say? I have given you the access to speak.
Okay. Thank you very much, sir. So actually, in most of the times we deal with life science data, and I'm a current graduate student, and I noticed that in most of vacancies that require wants to maybe to apply for PhD studentship. So most of the professors used to request that the adequate knowledge of Python and C++. We assist one to gain admission to maybe to their lab, things like that. So I want to really know how best to master this particular programming languages like C++ and Python, so that my chance of being admitted to highly ranked universities in the US can be succeeded.
I mean, like I guess I like a couple of avenues, but like number one, I might point you to like just doing a course if it's not like the course that I teach, a similar course. A lot of stuff that I've learned is also like web-based. So myself, I use Stack Overflow a lot as well. I kind of like managed to get myself into the couple of top 1% on Stack Overflow by sort of like asking enough questions and answering enough questions as well. So it's a combination of all of the web-based stuff and maybe a course or 1 or 2 courses as well. But the reality is like when you do the web-based things, even if you're doing it and you kind of want to teach yourself, is have an objective of what you want to get to. Like, I want to, I want to be able to download some data and, save this data into a file and do some processing and then produce this output. And that's going to be my result. And then go and actually execute and do that. And I'll probably say start first with Python before C++. Just because it's easier to get to your endpoint, starting with Python first. But by no means ignore C++ because it has advantages as well. But that's kind of like your path.
Right. Thank you, Isika. Martin, you can go ahead and ask your question now. Martin Christie, you wanted to ask a question?
Yes, I'm here. Hi, this is Martin. I'm from Copenhagen, Denmark, and currently I'm like doing BGB course in Careerera. So my question is like after doing this course, so which is the best position to apply?
So what are you doing the course in?
It's a data science course in it's post-graduation data science course, sir.
Okay. What's the question? Like,
Which is the best position to apply as a fresher?
it depends what field that you want to get into, as in a position to apply for a job, like in the job market, or a position to apply for like in academia, because they're kind of like different things as well.
It's as a job market.
Right. Which country are you from or at the moment, or where do you want to be? Because again, it's going to depend on, like, that's a tougher question, but it's going to depend on where you are. Obviously, I'm in the UK, and the London financial market is a major hub. Now, if you kind of like wanted to go and be in the fintech space, you know, a large number of them are kind of like they're in Silicon Valley, or they're in London, or they're in New York, or they're in Tokyo. So kind of like, one of the major cities, kind of like the obvious ones in reality. But again, it really depends on the company, and a lot of places now are becoming remote. I know that Holland as well, so Amsterdam for high frequency trading, for example. I've seen a few things come out of there, and also Dubai for crypto, which is something that's kind of like expanded and, you know, has come from nowhere in the past 10 years. So it depends on kind of like the asset class and where you want to be, and even where you are now.
Okay, sir, got it. And one more thing, can we get this PPT file also? Is it possible?
Can we get, sorry, what thing?
I'm saying, can we get this file which we are showing us?
Oh, the slides? I guess so. Why not? I could do. I think the course administrators.
Yep, that is no problem. And Martin, just to add to that, the session is live on YouTube right now. So we'll share with you the recording for today's session. Plus, you can anytime go to our YouTube channel or our LinkedIn page, and you can watch the video from there also. It's always an option. Okay.
Okay. Yeah. Thank you. Thank you so much.
Thank you, Martin. Thank you. So Martin, one of our students had a question, Darren. Now let me just see if there's anybody else who has any question. Otherwise, we are gonna go ahead and end today's session. If there's anybody who has a question, you can either type in or you raise your hand, and I'll give you the option to talk, and perhaps then you can ask. Anybody has any question? Well, I don't see any hands up. All right, guys, so I guess we are done. Thank you once again, everybody, for attending the session. I hope we added some value and we were able to go ahead and teach you something. Darren, do you have any last words to say to our participants and everybody watching online?
Thank you all for taking your time. I know that the World Cup's on, so you've probably foregone a game or two. I know I've missed a couple of good games there whilst this has been going on, so we'll catch the highlights. Look, I just hope that kind of like I partly inspired you. Like I've had an amazing journey, you know, and I probably wouldn't have swapped it for anything. And, you know, I wish I could just live for the next, I probably wish I could live for the next 100 years to see what's going to happen in the future. But certainly some of you guys are going to take the baton on, you know, and that kind of thing, and, you know, be handed on, and you'll be doing greater things, hopefully, as well.
All right, then, on that note, let's go ahead and end today's session. It was really nice connecting with all of you, and you have a wonderful day ahead. Bye-bye, take care, and see you. Bye.
Thank you. Bye.